We start our development of a numerical method for simulations of multifluid and multiphase flows by a short discussion of the governing equations. The development described here focuses on incompressible flows. Since for many problems of practical interest, this is an excellent approximation, and we start by developing a method for isothermal flows. The governing equations can be written in many different forms, and those different forms provide the natural starting point for different numerical methods. Here, we will focus on the integral form of the equations and the so-called single fluid formulation, where we write one set of equations for the whole flow field, including the different fluids. We start by a summary of the derivation of the governing equations. The governing equations are mathematical statements of the physical principles that we use to predict the evolution of the flow. For fluid mechanics problems, we generally use the principle of conservation of mass, conservation of momentum, and conservation of energy. Here we assume that the density of the material particles does not change as its location changes, and this leads to incompressible flow, where the volume of any small fluid blob remains constant. For incompressible flows, the pressure, used in the momentum equation, has a special role since it must take on whatever value needed to enforce incompressibility. For isothermal flow, the special role of the pressure allows us to leave out the energy equation, but for problems where the temperature changes, we'll need to bring it back. For flows consisting of two fluids with different properties, we also need to solve an equation specifying what part of the problem is occupied by which fluids, or where the interface separating the different fluids is. The conservation of mass equation is derived by applying the conservation of mass principle to a small control volume. Consider a control volume fixed in space and of an arbitrary but fixed shape. We denote the control volume by V and the control surface which separates the control volume from its surrounding by S. The mass conservation principle states that the rate of change of the total mass in the control volume, the time derivative of the integral of the density over the control volume, is equal to the net in or outflow into the control volume, represented by the surface integral of density times the normal velocity. Since we take the normal to be positive pointing outward, and inflow adds to the mass and outflow decreases the mass, we need a minus sign in front of the surface integral. Notice that the control volume can contain an interface, so the density can be different on different parts of the control surface. Using the divergence theorem and that the control volume is fixed in space, so the time derivative can be moved under the integral sign, the mass conservation equation can be written as one volume integral over the rate of change of the density plus the divergence of the mass flux, or the density times the velocity. We then expand the divergence, and realizing that the first two terms are the convective derivative, partial rho with respect to time plus the velocity times the gradient of rho, so we can write the convection of mass equation as the volume integral of the convective derivative of rho divided by rho plus the divergence of the velocity. If the density of a material particle remains constant, as it does for incompressible flows, then the first term is zero, and we are left with the volume integral of the divergence of the velocity being equal to zero. Applying the divergence theorem, this can be restated as the surface integral over the control surface of the normal velocity being equal to zero, or the volume inflow into a control volume is balanced by the outflow for incompressible flows. The momentum equation is derived in the same way. We focus on an arbitrary control volume of fixed shape and fixed in space. The rate of change of momentum in the control volume is given by the net inflow of momentum, the first term on the left, where rho u is the momentum, and multiplying that by the normal velocity gives the flux through the boundary, plus surface and volume forces given by the second and third term. For the surface force, we assume a Newtonian fluid where the stress is given by the pressure acting normal to the control surface, plus the viscous stresses given by the viscosity times the rate of deformation tensor, which is the symmetric part of the velocity gradient tensor. The full stress tensor also has stresses for compressing the fluid, but for incompressible flow this is zero and is therefore not included here. The body force generally includes gravity, and for immiscible multiphase flow we usually also have surface tension. We'll give the specific form for the surface tension shortly, but here simply split the body force into two parts. For more complex situation, we can have additional body forces, such as due to electric or magnetic forces, or we may have body forces such as centripetal and Coriolis forces that appear because we are in a moving frame of reference. For two-dimensional flow, tension on the interface is given simply by sigma times the tangent vector, here denoted by bold lowercase t. The force on a controlled volume enclosing a segment of the interface is the difference in the tension where the interface enters the control volume and where it exists at sigma t at 2 minus sigma t at 1. We can represent the total force on the control volume in several ways. We will in particular use that the difference in sigma t at the endpoints can be written as an integral over the part of the interface that is inside the control volume, which we denote by delta s. Using that the derivative of the tangent vector with respect to arc length s gives the curvature times the normal to the interface, bold N, and taking the surface tension to be constant, we can write the total force as the integral of sigma times the curvature times the normal over the part of the interface that is inside the control volume. We can convert the integral over the part of the interface inside the control volume to an integral over the control volume by multiplying by a one-dimensional delta function that is 0 everywhere except at the interface. Although we will not use this form for the numerical code, it's very common and sometimes useful in theoretical discussions such as those at the end of this lecture. For flows with two or more fluids of different but constant properties, we generally need to know what fluid is where. Thus, we need a marker function that is updated as the flow evolves. The various material properties can then be set as functions of the marker function. For two fluids, we use a step function that is 1 in one fluid and 0 in the other, and the properties take one of two possible values. To update the marker function, we start with the mass conservation equation and substitute the expression for density as a function of the marker function. Using that the convective derivative of the density is 0, we immediately get that the marker function is governed by the same equation, namely that the convective derivative is 0, or the marker moves with the fluid. That is, of course, something that we could have seen coming. If the material properties are constant in each fluid, as is the case here, the advection of the marker function becomes considerably simpler and we only need to know where the interface is. To sum up, the equations that we will be solving are the momentum equations for the two velocity components, subject to the constraint that the fluid are incompressible, so that the volume flow in and out of a control volume balances, and the advection equation for the marker function, which will then give the material properties of the fluid. Let me conclude the introduction of the governing equations by making a few points. First of all, the conservation equations for mass and momentum apply to any flow situation, including flows of multiple immiscible fluids. Secondly, for multiphase flows, each fluid generally has properties that are different from the other fluids, and the location of each fluid must therefore be tracked. And third, we usually have additional physics that must be accounted for at the interface, such as surface tension. The governing equation can also be written in differential form using generalized functions, as I will discuss briefly in the next few slides. Although we work with the integral form of the governing equations here, since that leads directly to a finite volume method, many authors prefer to start from the differential form. Indeed, my guess is that more papers start from the differential form than the integral form, even when finite volume methods are used. Since the marker function is discontinuous and the surface tension is singular, we need to work with generalized functions to be able to write down the differential form. To do so, we need to define the Heaviside step function in such a way that we can find its gradient. A particularly simple way is to define it as an area integral over the multiplication of two one-dimensional delta functions. Here x prime and y prime are the integration variables, and x and y are the coordinates of the point where we are sitting. If x and y are inside the area, the x and y will be equal to x prime and y prime, and the integral will be 1, but if x and y are outside the area, then the integral will be 0. The gradient is with respect to x and y, so we can bring it under the integral. However, since the gradient is antisymmetric with respect to the primed and unprimed variables, we can change the gradient to the gradient with respect to the prime variables, changing the sign. We now apply the divergence theorem to write the integral as a surface integral, or contour integral in 2D, and since the delta functions are 0 everywhere except where x, y are equal to x prime, y prime, we can drop the circle on the integral. By introducing local coordinates n in the normal direction and s in the tangent direction, we can integrate over the tangent direction and thus are left with the results that the gradient of the Heaviside function is equal to a delta function times the local normal. Here we take the normal to be positive, pointing away from the h equal to 1 region, so we need a minus sign. By applying the standard argument to the integral form, that the equations hold for an arbitrary control volume, so the integrand must be 0, we get the differential form of the conservation equations. These equations are essentially the same as for single-phase flow, except the material properties are step functions, and we must add a singular surface tension term. The momentum equations must, of of course, be supplemented by the incompressibility condition and advection equation for the material properties. We generally refer to this form of the equations as the one-fluid or one-field formulation. It is important to keep in mind that the one-fluid form of the governing equations contains no approximations beyond the standard continuum equations. They do, in particular, include the jump conditions that we would have to apply at an interface if we solved separate equations for each fluid region. We can extract the jump conditions by integrating the one-fluid equations over a small pillbox containing the interface. The box follows the interface, which moves with the fluid velocity, so we combine the first two terms into the convective derivative and then integrate. Most of the terms have a finite value and go to 0 as the size of the box goes to 0. The singular terms, however, do not do that, and we are left with a statement that says that jumps in the pressure and the viscous stresses are balanced by the surface tension. You know that we need to modify this argument slightly if there is mass transfer across the interface, such as for evaporation and condensation, and if the surface tension is not constant. We can also show that the one-fluid formulation contains the equations written separately for each fluid and the jump conditions by writing every variable as a function of the marker function and substituting the one-fluid equations. By grouping terms depending on whether they are multiplied by h2, h1, or a delta function, and using that each group must be equal to 0 separately, we recover the equation for each region plus the jump conditions. Once we have the governing equations and have decided on which form, such as the integral form, to use, we need a solution strategy. There are several possibilities. To solve for the flow, the governing equations need to be discretized both in space and time. To do so, we divide the computational domain into a finite number of control volumes for finite volume methods, or use a finite number of points to represent the flow if we are using finite difference methods. For flows with moving interfaces, solution methods can be divided in two major categories. We can solve separate equations in each fluid using a moving grid aligned with the interface where we apply the appropriate boundary conditions. Or we can solve one set of equations for the whole domain on a fixed grid and incorporate the boundary conditions directly into the governing equations. These alternatives are shown schematically here. In the left column, we use structured grid where the layout determines the relationship of each control volume to its neighbors. And on the right, we use unstructured grids where the shape and layout of the control volumes are arbitrary and we need to explicitly store information about their layout. In the top row, we align grid lines or control volume boundaries with the interface, but in the bottom row, the interface is independent of the grid lines. While the grids in the bottom row are usually stationary, the grids in the top row must change with time if the interface is moving. In our case, we will use regular structured grids where the interface can have an arbitrary orientation with respect to grid lines. This overall strategy is, by far, the most common and so far the most successful approach to simulating flows with sharp interfaces. Even after we settle on this approach, there are a number of alternative methods. Roughly speaking, the questions are what numerical methods we use to solve the Navier-Stokes equations and how we track the interface separating the different fluids. These are somewhat separate questions, and in the next lectures we will first develop a code to solve the Navier-Stokes equations and then present a few of the possibilities that are available for tracking the interface. We'll then pick one of them to implement in the flow solver.